This conference will now be recorded.
So we'll start with the session now. So in today's session, we'll be discussing about AHB protocol, the detailed features. We'll talk about architecture, components in the architecture, the ports or the signals, AHB ports, and the timing diagrams, features, AHB protocol. We'll also talk about interview questions. This protocol training could be spread over 1 or 2 sessions based on how we progress. And once we are done with this AHB protocol, we'll talk about AHB UVC development. UVC here stands for Universal Verification Component. Okay, so now let us start with AHB protocol. So in UVC development, what we will do is we will develop AHB master UVC and slave UVC. So master UVC behavior validated using slave UVC. So that is what we are doing. So now let us start with the AHB protocol understanding. AHB stands for Advanced High Performance Bus. That is why it is AHB. So first let us start with some protocol basics. What is a protocol? It is a set of rules for the various phases of transfer between master and slave component. You have a master and you have a slave. What are the guidelines that need to be followed and how the signal should be driven? Those set of guidelines is what we collectively call as protocol. There are two categories of protocols in VLSI. One is called as on-chip protocols, one is called as peripheral protocols. So there are two types of protocols. So set of guidelines which define the communication between master and slave component. Next, protocols are two types. One is on-chip protocols, one is peripheral protocols. As the name suggests, on-chip protocols are for communication, the protocols which define the communication of components on the chip. Peripheral protocols defines protocols which define communication of the components with components outside the chip. One is on the chip, inside the chip, one is outside the chip. Okay. Now, peripheral protocols are limited by space, limited by the available area, because we can't use too many ports. That is example, imagine a 40 port USB pen drive. Generally it'll have four wires, right? One is V plus, voltage, ground, D plus, D minus. That is what you see in the USB. But imagine a USB pen drive with 40 ports. It will be as big as my laptop, one side of the laptop. Hence, they're limited by number of ports. Whereas on-chip protocols, there is no limitation on ports, limitation on the port size, because the manufacturing, fabrication technology is so advanced that we can keep 1,000 pins in millimeter space or even less. That is not possible in case of peripheral protocols. So the manufacturing happens at so low level, that is at nanometer level, that you can keep thousands of pins in millimeter or lesser space. Now let us talk more about on-chip and peripheral protocols. Some of the examples of on-chip protocols are like AXI, AHB, OCP, PCI. It's not PCI Express. AXI stands for Advanced Extensible Interface. AHB stands for Advanced High Performance Bus. OCP stands for Open Core Protocol. PCI is Peripheral Component Interconnect. These are all on-chip communication protocols. Major problem with on-chip protocols is they're limited by frequency of operation. See, when you buy a mobile phone, it will come with a specific frequency, right? It will say it can be operated at 1 gigahertz processor. When you purchase a mobile, when you read the specs, you'll see that it will have 1.5 gigahertz quad core processor, something like that. That is where we are talking about the frequency of operation. Does it mean that AHB can't operate beyond that? Can't run more beyond that frequency? It's not that. AX and HB can run at any frequency actually. There is no theoretically there is no limitation on at what frequency AXI and HB can run at. They can run at infinite frequency also. But what is limiting them is the timing closure of the chip. We need to close the chip. Let's say we are what is timing closure means? There will be lakhs of flip-flops inside the chip. None of them should give setup or hold time violations at the specified frequency. As the frequency increases, chances of setup violation will increases. Then if setup violation happens, it results in metastability condition, where we don't know the output value of flop. Then whole chip goes to metastable state. This state is called as timing is not closed. This state is called as we are not able to close the chip timing at this frequency. So then what we do, what will be the resolution? Immediate solution is reduce the frequency and reduce the frequency of operation. Then to some extent the setup violations will be resolved. So as you keep reducing the frequency, setup violations will reduce. As you increase the frequency, chances of getting setup violation will be higher. That is what limits the frequency of operation. It is not the AX and HP which limit the frequency of operation. Now, so that is what I mean by limited by frequency of operation. In case of on-chip protocols, data communication happens in terms of transactions. We use the term transactions, whereas in peripheral protocols, we'll use the term packets and frames. If you remember Ethernet example, we used Ethernet packet. We didn't call Ethernet transaction. Whereas in AXI, we called it as AXI transaction. In these transaction happens in multiple phases, different phases: arbitration phase, request phase, data phase, response phase. All these phases are not applicable to all of them. let's say AXI does not have arbitration phase. There is no arbitration phase for AXI. For AHB, these two phases are there. This is finally called as response phase. And what I mean to say is 4 phases are not there. For OCP, again arbitration phase is not there. So based on the protocol, some of these phases will be applicable to some of these protocols. And there is a handshaking happens using dedicated set of signals. In case of peripheral protocols, what are the examples of peripheral protocols? USB, PCI Express, SATA, I2C, SPI, UART. These are all the examples of peripheral protocols. Major limitation of peripheral protocols is they're limited by number of ports. Because you can't keep peripheral itself means what? They come outside the chip. As you increase the number of ports, the packaging becomes more and more difficult. I mean, you cannot pack in this much. If you double the number of ports, you have to make the packaging this much bigger. Because you need to worry about the gap between ports, between this line and this line, how much gap I can give. So that is what limits the number of ports. In case of peripheral protocols, data communication happens in terms of packets or frames. Handshaking happens through using preamble and sync. There is no dedicated signals for handshaking. In case of peripheral protocols, there are no dedicated signals for handshaking purpose. There are no dedicated handshaking signals. Now we have been talking about so many protocols, 4 protocols here, another 6 protocols here. Like that, if you list down, you will probably come across 50 protocols in VLSI. So with so many protocols, how do you decide which protocol is suitable for you, which is the right protocol for you? So that is where we need to understand how protocols differ from each other. Protocols are differentiated based on 4 factors: the performance, power consumption, features, and pin count. Ideally, in an ideal protocol, we want this behavior. We want to get a highest performance at lowest power with the largest number of features, that is highest number of features, with minimal number of pins. So we want high performance, low power consumption, higher number of features, lower pin count. You can't achieve all of them best. If you want to get something best, you have to compromise on something. Let's say you want to go for high performance, you have to probably compromise on power consumption. Let's say you want to get both of them best, like you want high performance also, better power consumption also, then you have to compromise on the cost. Other factor will be the cost of implementation. Cost of implementation. Cost is somehow related to pin count. I mean, as the pin count increases, the design complexity increases, the cost will increase, right? So if you are trying to get, see, performance is nothing but features only, kind of. Features is not anything different. Features is directly related to the performance. Okay, if you want to get higher performance and higher power consumption, you will have to go with higher cost. If you want to get, if you are okay with lower performance, then you will get higher, better power consumption, you will get lower cost. I mean, only 2 things you can do best. One, you will have to compromise. So for example, Intel chips are the example. In Intel processors, what do you get? High performance, higher power consumption, but cost will also be higher. If you take AMD chips, for example, I don't know what is the exact scenario now, but earlier it used to be like high performance, low cost. But what was the problem with AMD chips back then? Higher power consumption. So if you try to get 2 things, you have to compromise on the third factor. So that is a little bit about protocol basics. Now, basically, based on in on-chip, you decide between AXI and AHB. So in on-chip protocols, we have to decide between, for on-chip requirements, on-chip communication requirements, we have to decide between where AXI, AHB, APB, OCP, PCI, etc. Even APB is an example. So how do I decide? How do I decide whether to go for AXI, whether to go for AHB? How to decide? First, understand the requirements. Understand the requirements. Do I want high performance or low performance? Are we or low performance? Because sometimes we are okay to get low performance also. Let's say you're typing in keyboard for a block which is reading my data, what I'm typing, it need not be high performance. Low performance is sufficient, because even if I sit throughout the day and type, I will not type probably 1 megabyte of data. Okay. And the power consumption and the cost wise. See, always this is the most important factor. Among all the things, this is the most important factor. Then we try to reduce these things. You don't start with low cost. See, your requirement will never start with the cost. Your requirement will always start with the performance. Based on that, you decide what is that you want to do for other things. For example, if I want very high performance, if you need to run a high-end applications, then we need high performance processor. So AXI is the protocol which works for high performance processors, high-end processors. That is what we call as application processors. In that case, we need to use AXI protocol. If the requirement is for a medium performance, is for medium or lower performance, okay, from a specific component, specific processor or a component, then we go with AHB protocol. Now, AXI and AHB are ARM proprietary protocols. That means any ARM processor you purchase, they will either work on AXI or AHB protocols. Okay, now we'll go into the AHB. I hope you got a basic overview of what is protocol, what are the categories of protocols, what is on-chip communication protocol, what is peripheral communication protocols, how do you differentiate between one protocol to other protocol, and what is again the difference between AXI and AHB. AXI is used for very high performance requirements, AHB is used for medium performance requirements. Now let's get into AHB basics. It's a ARM proprietary protocol. That means it is developed by the ARM company. The protocol behavior, how the address phase will happen, how the data phase will happen, what signals are there, everything has been specified by the ARM company. All ARM process will be either based on AXI or AHB. The interconnect is used for connecting multiple masters to multiple slaves. AHB based system architecture has below components: masters, slaves, interconnect. For example, this diagram, this is the interconnect. This line, what you see, thick line, is what we are calling as interconnect. This is called as AHB interconnect, since it's AHB protocol. This is called as APB interconnect, since it is based on APB protocol. If you are connecting AHB interconnect to APB interconnect, you have to use a bridge in between, which will convert AHB protocol to APB protocol format. So you see, in case of AHB interconnect, you are connecting one high performance ARM processor. Even though they are calling high performance, it won't be like application process. It will be mid-range process. I mean, what we call as M series or R series processors. See, I will tell you again further summary about that. ARM has three types of processors. One is called as A series, one is M series, one is R series. Okay, A series uses AXA protocol, M series uses AHB protocol, R series uses AHB protocol. So this would be either M series processor or R series processor. Had it been A series processor, A means application specific. So A series stands for application series. I think it stands for embedded series. This stands for real series, real time application, real series. Okay. So based on what is your requirement, you either go with application, M series or R series. Based on that, the protocol will be decided. Let's say had it been A series, then I have to compulsorily use AXA interconnect here. Because this would be AXA protocol, I have to use AXA interconnect here. Since it is either M series or R series, I'm using AHB protocol here. And you see these components, UART, timer, keypad, and PIO. These are low performance components. They don't need to be really connected with AHB. They can be connected with the low performance protocol, that is APB protocol. Why we need low performance? Because these components, keypad, PIO, UART, timer, they don't require too much data transfer. They hardly require data transfer to the tune of 8 bytes per second or maybe 100 bytes per second. That is a very low speed. See, now we are talking about gigabytes per second. Imagine that with respect to 100 bytes per second. That's a very low rate, right? So for that purpose, we go with APB protocol. Whereas high bandwidth RAM, DMA master, high bandwidth memory interface, they require a huge data transfers. Hence, we connect them to AHB interface. Accordingly, based on the requirement, we decide whether they should be connected to AHB, whether they should be connected to APB. Now, going back to this, interconnect is used for connecting multiple masters to multiple slaves. I hope you understood the requirement of interconnect here. Multiple masters connected to multiple slaves using one common interface. AHB based system architecture has following components: masters, slaves, interconnect. Interconnect acts like a slave for the AHB master connection. See, you are connecting a master to interconnect here. In turn, interconnect will act like a slave here. It will act like a slave here. It is connecting to on-chip RAM. It will act like a master here. Here it will act like a slave. Because it is a master, it will act like a slave here. Because it is a slave, it will act like a master here. So based on what is the other component behavior, the interconnect will either act like a master or slave. Next. Interconnect acts like a master for AHB slave connection. Interconnect routes the master request to the target slave, routes the slave responses to the correct master. See, what is the role of interconnect is very simple. When a transaction happens from master, it has to decide whether it has to be sent in this direction, this direction, this direction, or this direction. For that purpose, there will be some decoding logic inside this. Even though it's a line, it is not really line. It has got some decoder plus multiplexer. The interconnect is made up of decoder plus multiplexer logic. So it decodes incoming request address and figures out in which direction request should be routed. It decodes incoming response. I mean, there is no decoding. It automatically figures out. It automatically knows in which direction response should be routed. Now the question automatically will explain. I mean, at any time, one master, one slave connection got established. So the master knows. So the interconnect knows which is the master active now. In that direction, it will send the response. So let's say if I had initiated in this direction, for example, in this direction, when the response comes, I know that response has to go here only, because no other component is acting like a master at that point of time. That information is also tracked by the interconnect. It knows who is the current active master. Next. So interconnect routes the master request to target slave, routes the slave responses to the correct master. Next, this is how AHB based system architecture diagram looks like. You go with AHB if you want high performance, pipelined operation, burst transfers. I mean, how it gives high performance? Through pipelined operations, burst transfers, multiple bus masters, and split transactions. APB, it is used for low power requirements. The primary requirement where you go for APB is because you want low power. And it latched address and control, simple interface suitable for many peripherals. Based on the requirements, either you go for AHB or APB. See, the point here is when you are connecting one component, let's say I introduce one component called as multimedia card controller. When I want to connect multimedia card, I have to use multimedia card controller. Now I have to decide whether to keep it here or whether to keep it here. That I will decide based on what is the performance requirements about of the MMC. Let's say if I'm going to use MMC frequently in the current chip, I'll have to connect it here. No, if I'm going to use it very rarely and the requirements will be less, then I'll connect here. So based on that, we decide where to connect it. Okay, now let us talk about AHB transfers. AHB transfers happens in 3 phases. What are the 3 phases? Can you please read them once? One is arbitration phase, one is request phase, one is data phase. Arbitration phase is where we decide which master has the grant, which master is given the grant. Only that master can initiate the remaining 2 phases. So to do these phases, first master has to get the grant. So let's understand these phases now. Arbitration phase, master asserts a request signal to the arbiter. Arbiter will grant access to the request. Requesting master will grant access to requesting master. What is arbitration phase? Let's understand. If this is the interconnect, if there are 3 masters, I think let's draw the diagram. It will be, because we are going to use this throughout the session. Let's take paint and draw the diagram. One interconnect. Okay. Let's take a masters, 3 masters. Any number of masters. You may say Y3. You can take any number. 3 masters. And let's say some few slaves. These are connected to interconnect. This protocol will be AHB protocol because These are all AHB based components. I mean, their communication happens with external world through AHB protocol. These are called as masters. M1, M2, M3. This is called as interconnect. Interconnect is nothing but decoders plus muxes. These are masters. Sorry, slaves. Slave 1, slave 2, slave 3, slave 4. AHB protocol supports system architecture with maximum of 16 masters and 16 slaves. Okay, that this limitation is due to the load factor, the capacitance that gets added as we connect more components to the interconnect. So as you start connecting, at one point the signal integrity gets impacted, because as you connect more and more components, the load increases and the signal behavior gets disturbed. So because of that reason, they limit it to 16 masters and 16 slaves. Now in general, we won't come across any requirements bigger than this. Even if you take the most complex chip available in the world, you will never require to connect 16 masters and 16 slaves for AHB architecture. If at all you have to do more than that, let's say you want to connect more than 16 slaves, you have to use bridge, connect one more interconnect, on that you connect remaining slaves. Now question comes, what if I need to connect more slaves than 16? How do I do that? Use one more interconnect, connect this to the original interconnect, the first interconnect, using a bridge. Which bridge? AHB to AHB bridge. So connect all the slaves to, connect remaining slaves to second interconnect. So what does it mean? In this case, if you want to connect more interconnects, what I would have done is I would have connected one more interconnect like this. Assuming that I have done till S15, I will connect this as X16. So this will become slave 16 through a bridge. Here I will connect more slaves, S17, S18, S19, S20, like that. So that is how you can extend the AHB architecture, number of slaves. So we will use this diagram to understand all our use cases of AHB. What is arbitration phase? In this system, assume M1 is like a processor, M2 is another processor, M3 is another processor. It is possible that even this wants to do a request, this wants to do a request, this wants to do a request. Request means either write to the slave or read from the slave, one of them. What does it mean? I'll just give you one use case example. One processor wants to play music. I mean, we want to play music. The music is present in this slave, MMC card or some pen drive it is present. So master 1 wants to read the data from slave 2. So that becomes one use case. In another use case, you want to print some document. Let's say this is the printer connected, and this master is trying to give the data to it. So like that, based on the requirements, there will be different masters will interact with different slaves, and they can happen parallelly, right? It's not like you while doing one work you can't do other work. So in those cases, how does this AHB works? That is where comes a concept called as arbitration. What is arbitration means? Why do you need arbitration? Can someone tell me why, when do we need arbitration? When there is a resource,
to, to select the particular resources, sir.
multiple components wants to access the same resource, but only one can be allocated with the resource. Then comes the arbitration. This is where we need arbitration. Now in our example, what is the resource? In AHB example, what is the resource? Resource is the interconnect and access to the bus. Access to the bus is the resource. Who are the components? What are the components that need access? Component that want access. What are those? Can you tell me from this diagram which are the component who want access to the bus?
Masters.
Masters.
Slaves, sir.
Not slaves. Masters. M1, M2, M3. Not slaves. It is the masters who want access to the bus. Now there is one resource. Only one interconnect is there, right? And there are three masters who may want to access. And it is possible that in some cases, few masters may not want access. But even if there are two masters who are trying, still it is an arbitration, right? Even if two people are fighting for same resource, it is still arbitration. You don't need always three people to fight. So in those cases, you need an arbiter. So here, for this reason, we need a arbiter. Where is arbiter present? So what is the role of arbiter? Role of arbiter is to follow some guidelines, allocate the resource to the requesting components based on the guidelines. What is the, I will give you an example. There is a car, okay, and two people want to use that, okay, the car. So there is only one resource. Now what we will do is, along with the car, we'll keep one person here who is going to give the key to either this person or this person. In this case, what I would have done is, we would have given him some guidelines. If this person comes and if this person comes, this person will get higher priority on other person. Let's say if both come at same time, what should you do? If they come one after other, whom to give grant? Let's say if he comes first, don't do anything, just give him the grant. But what if both of them come at same time? Then whom to give grant? So like that, we would have given him the guidelines. Based on that, this person will decide whom to give the key. But understand, he is not going to drive the car. This person who is arbiter, even though he has the car key, he is not going to drive the car. He is only acting like an arbiter who is going to make a decision whom to give grant. So we'll talk more about arbitration in later slides, later part of this session. I hope you understood why we need arbitration. In master asserts a request signal to the arbiter. Arbiter will grant access to the requesting master. Arbiter is present inside interconnect. Interconnect itself has one more component called as arbiter. So in summary, what is interconnect? Interconnect is arbiter plus decoders plus multiplexers. Next, what are the signals used for this arbitration phase? HBus request. Okay, HBus request is a master is requesting to the interconnect that I want bus request, I want access to the bus. HLock means
master is telling to the interconnect that I want to do a locked transfer. If you give me the grant, I want to do a locked transfer. Master X, it indicates that which master is active now, which is the master that has been given access. Grant is the one which tells it is driven by interconnect to tell who has been given the grant. Split is a different concept. I will explain that later. Okay. Request phase. Once arbitration is done, so during arbitration, we decide among these masters whom to give grant will be decided. So whoever has got the grant, let's say either M1, either M2, either M3 got the grant, that specific master will initiate a request to the specific slave. That phases happens in two phases. That transaction happens in two phases: request phase, data phase. So essentially, AHB communication happens in three phases: arbitration phase, request phase, data phase. So let us understand what happens during the request phase. In AHB, it happens multiple times. In AXI, it happens only once. The request phase happens only once in case of AXI. What is request phase? The granted master, whichever master that we have given grant, drives address and control information to the slave, initializing a new transfer. What are the signals involved in request phase? H address, H write, H trans, H burst, H size, H prot. These are the signals which are used in request phase. What is data phase? Data phase, by what happens? Master has initiated a request has reached here. Now it is the interconnect which will decide through decoding logic, decoders, it will decide whether it should go here, whether it should go to slave 2, slave 3, slave 4. Let's say in this case it is targeted to slave 1. The slave 1 will complete the data phase. I mean, master, if it is right, master will give the data. If it is read, slave will give the data. That phase is called as data phase. So what is data phase? Slave accepts HW data from master in case of write transfer, issues HR data from slave in case of read transfer. Data phase is complete only when H ready is 1. When H ready is equal to 1, that is when data phase is complete. What are the signals involved? H ready, HW data, HR data, H response. These are the signals used. One thing you should notice is all AHB signals starts with H. H address, H write, H trans, H burst, H size, H prot, like that. Okay, some more basic concepts about AHB. You can divide address and control signals. I mean, the signals are address and control signal, address, direction, width of the transfer. If the transfer is part of the burst. Okay, burst transfers are two types: incrementing bursts, which do not wrap at the address boundaries; wrapping bursts, which wrap at the particular address boundary. I think this is out of context for us now. When we go to the burst transfers, we'll discuss that. Transfer happens an address and control cycle, one or more cycles for data. All slaves must sample the address during address and control cycle. Data cycles can be extended by using H ready signal. H response, I think this overall slide itself is not relevant. Okay, now let us talk about differences between AHB and AXI. AHB protocol supports maximum of 16 masters and 16 slaves. Even in AXI, we'll have similar limitation. If you want to connect more components, you have to use another interconnect and connect to that. AXI allows all masters to communicate with all slaves at same time. You understand the point? Same time. Why it is work same time is AXI has AWID, WID, BID, ARID, RID. This ID, yeah, associated with each channel, associated with each phase of transfer, which gives with unique ID, which gives unique ID to each transaction or each phase. allowing multiple transactions to happen concurrently and in any order at the same time. What is it? AXI has a concept of ID, which is identification, associated with each phase of transfer, which gives unique ID to each transaction or each phase, allowing multiple transactions to happen concurrently at same time. Whereas AHB does not have ID. Like AXI has IDs through which you identify this transaction belongs to this transfer belongs to this transaction, this response belongs to this transaction. But in AHB we don't have ID. So AHB does not allow all masters to communicate, rather I would say not all, multiple masters to communicate at same time. Only one master can do the control, can do the transaction at any time, and it will have control of interconnect at that point of time. Only one master can do the transaction at any point of time, and it will have control of the interconnect at that point, at that point of time. The master which gets interconnect access is decided during arbitration phase. Multiple masters trying to access same resource, hence arbitration is required. We already discussed why arbitration is required. Arbitration is either based on priority or round robin manner. I mean, round robin means what? What is priority means? Priority arbitration means among M1, M2, M3, whichever master has highest priority, that master will get the grant. What is round robin arbitration means? Among M1, M2, first grant will be given to master 1. Once M1 completes transaction, M2 is given grant. Once M2 completes transaction, M3 is given grant. Once M3 completes transaction, M1 is given grant, so on. This concept is called as round robin arbitration. Both can work. Okay, that is about it. Once master is granted access to the interconnect, it starts doing request phase and data phases. Both can work at any frequency theoretically. I mean, see, theoretically, AXI and AHB can work at any frequency theoretically, but timing closure is the limiting factor. Because of that, we are able to only operate at 1.5 gigahertz or 1 gigahertz like that. Now, whenever we will go to the next topic, that is handshaking. Whenever we learn on-chip protocols, anytime we learn on-chip protocols, the most important thing we need to learn is how handshaking happens. Handshaking is a mechanism through which master and slave talk to each other. In AHB, handshaking signals are H-trans and H-ready. H-trans is issued by master to convey its state to the slave. I mean, master issues H-trans to indicate in what state I am. It will tell what I'm in: idle state, I'm in busy state, I'm in non-sequential state, I'm in sequential state. So whose state is it? Is it the state of a master or slave? Can someone tell me? So when I say idle, when I say busy, when I say non-sequential, sequential, whose state is it? Is it the master state or slave state?
Slave, sir.
It is the master state. I don't know how do you don't even focus in the session. It is issued by master to convey its state. Who is its master? To the slave. So if it is idle, it is telling that master is not doing any transaction. It is telling that I'm in idle state. Now master is in idle state. That means what? Master is not doing any transaction. Also, there is no transfer in progress, to indicate that master will drive H trans equal to idle. So there is a signal from the master. It will be output. See, that will be H trans will be output of this. H trans will be output of this. H trans will be output of this. Through that, it tells what is the state they are in. But it can complete data phase of the previous address phase. Whatever data transfers that are pending, it can complete, but it cannot initiate any new transaction. The whole point is what? It can't initiate any new transaction, but it can complete the ongoing transaction. Second, it can be in busy state. What is busy state? Master is in the middle of a ongoing transaction. At this cycle, it is busy, hence can't do address phase. At this point, ongoing transaction, at this cycle, as of now, just for temporarily, it is busy. Who is it here? Master. Hence can't do the address phase, to indicate that it will go into busy state. I mean, why it would be busy? It is addressing some other request, some other instruction, hence it got busy. But it can still complete the data phase of the previous address phase. Whatever data transfer that is from the previous transfer, it can complete it. Busy must be followed by either busy or sequential of H transfer. I will talk about this later. The third state is, I think let's remove this because it's unnecessary. Third is non-sequential. Non-sequential indicates it is the first transfer of the burst and only transfer in the single transfer. I mean, used by the master to initiate a new transaction. It is indicating that I'm initiating a new transaction now. So it is the first transfer of the burst or the only transfer in the single transfer. So basically, simple. It is used by master to indicate that I'm doing a new transaction. What is sequential means? Through non-sequential, you said that it is the first transfer. Sequential means what? Current transfer is related to previous transfer. Current transfer is part of the ongoing transfer. Whatever transaction is happening, I am doing this transfer as part of the ongoing transaction only. Transaction. So who drives H trans? Who drives master or slave? Master. It is from master to slave. Who gives H ready? Slave. So slave will convey its readiness to respond to the request. By asserting H ready. If H ready equal to 1, H ready equal to 1 means it is ready to respond. If H ready is 0 means it is not ready to respond. If H ready is 0 means slave is not in a position to respond to the request. If H ready is 0 for 2 clock cycle means 2 wait states are introduced. It means we are waiting for 2 cycles, so that is called as 2 wait states. Master will issue wait states by driving H ready equal to busy for required cycles. Let's say if you want to introduce the wait states from master, you keep busy. If you want to introduce wait states from slave, you keep h_ready equal to 0. Idle can't be driven while transfers is in progress. Every new transfer has to start with non-sequential type. So some basic guidelines are there. If there is an ongoing transfer is there, you cannot drive h_trans equal to idle in between. You can only drive busy in between. Every new transfer has to start with non-sequential type. So when we go to the timing diagram further, you'll understand all these concepts. These are very simple concepts. These terms, because these are all new to you, idle, busy, non-sequential, sequential, h_ready. Hence, you may be finding some difficulty, but once you go through the timing diagram, you'll find it quite easy to understand. Okay. Now that we have understood that,
Now that we have understood AHB protocol happens in 3 phases and how the handshaking works, let us go ahead and understand different phases of the AHB transfer. First, let us start with arbitration phase. Can you please read these notes once? Arbitration phase. Okay. So Arbiter grants bus access to the priority master requesting for bus. Arbiter also receives requests from slaves that wish to complete split transfers. Again, I will explain what is split transfer, everything later. For now, remember that there is a set of guidelines that Arbiter has to follow. Based on that, it will decide which master to give the grant. In this context, there are various signals are used. H bus request X. What is X indicates here? Let's understand. Arbitration phase signals. So X means what? H means AHB. Bus request means what? Signal to request the request for bus. X means what? Master number. See, there are AHB interconnect has multiple masters connected. X indicates the master that is making request. This signal will be from, what is the direction of this signal? Master to interconnect. And maximum of 16 bus masters can be there. What is H lock X? The lock signal